I think we are approaching a good number of people. My name is Fernando Perez Cruz. I am the Chief Data Scientist of the Swiss Data Science Center, and I will be conducting the presentation together with some of my colleagues. So I will want to introduce you first our Executive Director, Olivier Verschuher, who say the introduction to this presentation. Olivier, the floor is yours.
Thank you very much, Fernando, and good afternoon, everyone, and welcome to this Project Information Day of the Swiss Data Science Center. As many of you know already, this is an annual event that has been held for several years now, and it provides an opportunity for an exchange of information on the research projects that have been selected in a previous call, and an introduction to the new call for collaborative research project in data science. So without further ado, again, welcome, and thank you, Fernando, Guillaume, and the rest of the team for hosting this event. Back to you, Fernando.
Thank you, Olivier. So for the event today, first we will have an introduction of what SDSC is, as some of you might know, but not everybody might know. And then we will present the outcome of the last year call, and then present how the new call is going to be carried out. So Guillaume Nowosinski is the Deputy Chief Data Scientist, and he will do the first part of the presentation, and then some of us will continue after this presentation. Guillaume?
Thank you, Fernando. So I'm going to share my screen. And so you should see my slides. Is that right?
Yes, we do.
Okay, great. So I'll start by saying a few words about the Swiss Data Science Center. So the Swiss Data Science Center was created in 2017 as an ETH domain initiative to accelerate the adoption of data science, both in academic research and in the industry. Today, the SDSC has a little more than 75 employees, with offices at EPFL, ETH Zurich, and recently a small office at PSI. There are three main teams at SDSC of roughly equal sizes. So the academic team that is working primarily on the collaborative project that we will present in this webinar, with teams of scientists from ETH Zurich, EPFL, and the 4 federal research institutes. The industry team that works with industrial partners, primarily to help them define their data science strategy and to train data scientists that will form their data science team if they decide to build one. And then the Ranku team, which is our engineering team, who is developing a tool for workflow management in collaborative data science projects, and I'll say a few words about it. So let me talk first about academic research collaborations. We're really talking about the collaborative projects of the SDSC, which are the object of this call. So the SDSC has a double mission here. The first is to organize the reviewing process of this call, that is, review the projects that are submitted and appeal to external reviewers to do this process. And then once projects are selected and funded, the SDSC is then taking part in the project as a collaborator to the applicant. So this is the 6th call for projects. So in the 5 previous calls, we have carefully selected 73 2-year projects from a total of more than 300 submissions. And so out of the 73 projects, there are 30 that are ongoing, 22 that are now over, and there are 21 that are about to start. So these projects have led today to a little more than 50 publications in journals from different domains, and a little more than 25 papers in computer science conferences that concern publication of more technical methods and work. On the left, at the bottom, you can see a distribution of the topics of our collaborative research project. And you can see that the two main ones are environmental science that cover climate, atmospheric science, work on biodiversity, and health and biology, which is obviously quite important as well. In the table in the middle, you can see the distribution of the number of PIs from different institution whose projects were undertaken, and the number of the distribution as well of their partners. On the right, this is to illustrate how closely involved we hope to be in the project. So this is here we see in the picture one of our data scientists who is working on the Smart Air project with Professor Thomas Rösgen at ETH Zurich. This is a project on a wind tunnel where we'd like to design adaptive measurement, to design an algorithm that performs adaptive measurement to estimate as efficiently as possible the airflow around an object. And here our data scientist is using the measurement probe to get a sense for how this is working. And since this was done during COVID times, he's wearing a mask. A few words about industrial collaboration. Again, this is to work with individual companies to help them define their data science strategy and what are reasonable expectations from data science, machine learning, or AI. We help them develop technical solutions for specific challenges, so specific problems that also help them understand what to expect. And then we help them to hire jointly with SDSC data scientists that are coached and trained throughout the process. You see two illustrations. At the left, this illustrates a collaboration with Lonza, where we used multiplicative LSTM to train models that predict for proteins directly from the sequence. What are some, to predict, yes, from the sequence, what are some properties of these proteins, in particular properties that are relevant for manufacturing? And at the bottom right, this is an illustration of a project with Bühler, in which we help design a data-driven optimization method for cooling in the context of die casting. A few words about Renku. So if I have to define Renku in a single sentence, I would say that Renku is a data science workflow versioning system. If you're familiar with Git, which helps you keep a version of your code, the idea of Renku, which is actually built on top of Git, which uses Git, is to have a versioning system, but for the entire data analytics pipeline. So in addition to having your code under version control, your data is versioned as well, intermediate results are versioned as well. And the platform basically keeps track of the dependencies between data, algorithms, and results in the form of this graph that specify which data should be used as input of each algorithm and what are the outputs. The idea being that when data is updated or when code is modified, it is very easy to reproduce specific results in the graph by running only the parts of the computation that are needed and without having to rerun the entire pipeline. And among the other advantages, this graph is also very helpful to be able to propagate metadata in the graph, which makes it easier to abide by the FAIR principle. So this is it for what I wanted to say. I'm gonna let Fernando take over here. Fernando, please. And we can't hear you.
Thank you, Guillaume. I now gonna move to present the previous call for project. Can you move to the next slide, please? So in the last year call, we've from the last 3 years, we've been increasing the number of proposals from 42 all the way to 75 last year, and the number of full proposals have increased from 28 to 53. We've been plateauing in the last year, which is a good sign that we are well known within the 2 universities and the 4 research institute. There is also a lot of people interact with us before the call, and we will be very happy to answer any of your questions, either in the pre-proposal phase that we will present at the end, and also we engage with everybody in the final phase, because for the idea of this call, which is the collaboration with SDSC, is we are not only giving you funding, but we're giving you funding as a form of a person that is going to be working with you hand in hand in order to realize your scientific goals. In the last call, among the 53 proposals, I think it is important, is there is 9 people that were working with us before that reapplied and that wanted to keep on working with it. There were also 12 resubmissions, not only from the previous call, I mean, not only for the 2 previous calls, but even from the past. And we have an increased engagement with the research institute that were all the way to 19 proposals last year. We were, and this is something that we will see later, we had a track that was co-funded by PHRT that had 6 submissions, and another track with the largest scale infrastructure that had 6 submissions. Those 2 tracks are also available this year. Can you move to the next slide? And now, just to show the breadth of the type of projects that we have, I had a couple of, I have 5 projects here to represent the work that we've been doing. So we have this biodetect project that is being run by BSL and EAWAC, in which one of the part of the project is having cameras in the Amazonia in order to trap hummingbirds. And the goal of that thing is not only to detect when there is a hummingbird in the picture, but also to detect one of the over 200 species of hummingbird. In the project to the right is a project in which we're using is a measuring device in order to look inside the body for a few millimeters. The skin is excited using laser, and then the signal, the response of the body is using acoustic sensor, and that's the name of the optoacoustic project, and allows you to see the veins that are right under the skin. The objective here is to get a better reconstruction only when we have partial view of that veins. In the next project, it's an SPEC project, is trying to understand how the long-term weather prediction can be done from the stratospheric events, and especially the split of the vortex in the North Pole during the winter months, that whenever that split happened, roughly a month afterwards, we have a very cold event, either in North America or in Europe, and then trying to understand why this is happening, and if we can predict weather on a longer time scale than a few weeks up to a month or of 2 months. In the 2 projects that we have on the lower side, we have a project with the transmission and electron microscopy. The idea here is to be able to use machine learning in an electron tomography, and the goal here is that you will have samples from solids, including volcanic rocks, in which we want to understand what is the composition of that from the tomography, and we are developing machine learning algorithm in order to do so. And the last project that we have in this slide is talking about the narrative in law and politics, and the idea here is to use machine learning and causality to understand the text in political speech and judicial speech, how the way that the judges or the politics write and express themselves in order to find causality and understand the way that they communicate with the public. This is just to give you a little bit of the breadth of the projects that we have. I think Guillaume mentioned at the beginning, we have a strong focus in environmental and medical, but also we are doing things in politics we are doing things in physics, we are doing also engineering projects too. So with this, I finished my presentation. Now our lead data scientists are going to present the projects that were just selected that we will be starting this summer. So I will start with Michele Volpi will present 2 examples of the projects that we will start in a couple of months.
Yes, thanks Fernando for the introduction, and good afternoon everyone. So I just want to give you like a quick overview of two projects that are going to be have been accepted last year. That both of them relate at large to environmental sciences, and the first one is going to be is led by Dr. Fabian Walter from the WSL Institute, and it's titled Data Science and Mass Movement Seismology Towards the Next Generation of Debris Flow Warning. So as probably some of you know, debris flows are a mixture of rock sediment and water that can actually get up to very impressive speeds and have like an immense destructive power. The problem with active monitoring of that is that usually the mobilization zone of such phenomena is in remote areas, high up the mountains, and quite inaccessible areas. So the idea of this project is actually to deploy seismometers around the area and use the signals measured by those seismometers to characterize not only the mobilization of those debris flows, but also characterize what are the processes leading to an accumulation of material, which in turn will lead to a mobilization of debris flow. So the idea is to build machine learning methods that, based on classification and time series segmentation, that actually allow to detect different mass movement typologies, and to be accurate enough to provide early warning systems with significant lead time with respect to current techniques. And in principle, the knowledge that will be implemented in those models and the knowledge that will be extracted by those models will probably be leading us to be able to deploy such systems also to other catchment areas with different geologies, and hopefully provide solutions to monitoring also to other locations. The second project I want to mention is a project that's going to be led by Professor Achim Walter and Dr. Lukas Roth here at ETH Zurich, and is titled Extracting Dynamic Idiotypes from Seasonal Image Time Series of Wheat Taken in the Field. So for this project, as you know, wheat is one of the most important sources of food in the planet, but it's yet unclear how we should deal with climate change and adapt cultivations to face that. So the goal of this project is actually to use dense image time series as acquired by the field phenotyping platform from ETH Zurich that basically monitors with a very regular time interval around 350 genotypes of wheat, and basically replace the existing standards basically to analyze the relation between these genotypes, their phenotypes, and their dynamic the growth rates. To replace this very laborious and sequential pipeline with an end-to-end system. And basically the idea is to actually implement convolutional and recurrent generative machine learning neural networks, whatever you call it, and basically to see whether we can actually approximate specific plant traits, so for instance, yield, protein content, earliness of blooming and all of that, and hopefully being able to relate the learning of those models to some traits that relates to growth dynamics, which in turn will probably give information to experts and breeders to come up with maybe new types of wheat that are maybe more robust to climate change. And that would be it from my side.
Thank you, Michele, for your presentation. The next set of projects are going to be presented by Katia Klimova, which is also a lead data scientist here at ETH Zurich. Katia, the floor is yours.
Thank you, Fernando. Hello, everyone. And so the first project on the slide is predicting subclonal drug response from single-cell sequencing for precision oncology, which is led by Dr. Jack Kuipers. And this project is co-funded with PCRT. And so the project is addressing a fundamental problem of creating a targeted therapy in precision oncology. And so the cancerous tumors consist of heterogeneous cells, and some of subpopulation of the cells are less responsive to treatment than, and so for the treatment which targets only one type of the cells. And the aim of this project is to identify the tuber composition and uncover the mutation history based on single cell DNA and mRNA data. So additionally, it is planned to build and validate drug prediction models at the level of tumor subclones, given the drug response data. And this way, it would be possible to design targeted treatments for the full composite tumor. And the second project is machine learning for component fatigue prediction in hydropower generation. And it is led by Dr. Elena Vagnoni from PFL. The main goal of this project is to model and minimize damage due to fatigue in the several parts of hydraulic machine, namely in hydropower Francis turbines, which you can see on the pictures. And this project is built around the data of runs of several reduced scale copies of hydropower plant machines, which are at the PFL. And these runs are in different regimes, in steady state and transient regimes of the control parameters. And one of the challenging parts is of this project is to formulate and to solve a control problem aiming to minimize damage during transient regimes, since the constraints on the control parameters are changing in time. And development, so the methods which would be developed could potentially help to improve the efficiency and operational safety of the hydraulic system, and also to explore the unknown operation regimes and decrease the cost of the maintenance. Thank you.
Thank you, Katia. So the last presenter will be Benjamin Behar, which is the group leader at our team at PSI, and he also will present two of the projects in the FIFCO. Benjamin, the floor is yours.
Thank you, Fernando. Hello, everybody. So just continuing with the examples. So the first project that I'm presenting is with Professor Luc Tevena, who's the head of the group for fiber optics at EPFL. And the idea in this project is to use precisely fiber optics as a mechanism for sensing the environment. That's why the title is Data Analytics for Distributed Optical Fiber Sensing. Essentially, the idea is to deploy these optical fibers through an area that you would like to monitor. And by observing the properties of light as it propagates through the fibers, you can sense or pinpoint or detect changes in the environment. And this is the principle that is illustrated in this figure. So basically, we probe these fibers with a pulse of light. And along the length of these fibers, there are a number of scatterers that are randomly distributed along its length. And in principle, there is no direction that is preferred for the scattering of light. So when some event is happening, let's say an avalanche or maybe a landslide or maybe an increase in the temperature or events like that would affect the physical properties of the fiber, then the refractive index of the fiber would change accordingly. And we should be able to pinpoint to the places where these changes are happening. The process of probing these fibers is, as I said, you inject the pulse and then you observe the intensity of light that is being backscattered. And this can be seen as a fingerprint that characterizes the fiber. And we would like to detect anomalies along the length, of this fingerprint that is being obtained. The current approaches require probing with multiple frequencies, and it's a difficult iterative process that involves also the phase retrieval problem, because as you can imagine, it's lost in the sensing model. And we would like to use machine learning to precisely learn this fingerprint, this representation, such that whenever there is one of these anomalies or anomalous events, we would be able to directly pinpoint to the right location. The second project that I am describing is with Dr. Elisabeth Müller at PSI, who's the head of the group for electron microscopy and diffusion. So here, the goal of this project is to increase the resolution of this electron microscope that use a particular type of detectors. The project is called Increased Spatial Resolution in Electron Detectors through Machine Learning. And the idea here is that we are using these hybrid pixel detectors, which offer very high sampling rates, so we can do very fast acquisitions. And also they are good because they allow sensing of a high dynamic range, so of energies from very low to very high energies. The problem is that when an electron hits the detector, It follows a random track, and this you have an illustration in these figures. On the bottom, you have a view where you would see the depth and also the XY plane of the detector. So these tracks, as you can see, they're pretty much random, and this effect is more pronounced at low energy, so at the lowest SNR regime. Also, the deposition of energy as the electron hits the detector follows some diffusion process that is depending on the depth, and typically most of the energy is deposited towards the end of this track. On the right, on the bottom right, you have an example of what would be one of the images that we would be looking at. So, and you have marked with a cross the hitting point of the electron, and you see the intensity of the energy that is being captured by the detector. So in this project, again, we can think of it as a problem of super resolution. We would like to determine what is the entry point of the electrons with a resolution that goes beyond what is dictated by the pixel size of these detectors. And for that purpose, we would like to incorporate the knowledge about this diffusion energy deposition process together with machine learning methods that we can train for that. Thank you.
Okay. Thank you, Benjamin. Also, we have asked all our PIs to record a 2 to 2.5 minutes video presenting the projects. All these videos are going to be shown in our webpage, but we want to show you one of them by Paolo Benetti, just so you get an idea in their own words what the project is about. So can you share the screen, Guillaume, or do you want me to do it?
Sure, I'll do it. I hope the sound will work, but
you need to share the sound too when you share the screen.
Yes. So if you just give me 1 second.
Okay, and after this video, I mean, we asked for all the videos, but we're not going to show all of them because then the event will take too long. And then we will present the call, and then we will be open to your questions.
All right, so I'm sharing again. Share screen and share sound. It's asking me a password. Interesting. Well, I assume the password isn't going to be displayed.
Okay.
Should be good.
Yes, we're good. We can see the screen. Can you pull it full screen?
Yes. All right.
My name is Paolo Benetti, and I am a research scientist at EPFL. Together with Professor Andrea Rinaldo from EPFL, Professor Jen Kirchner from ETH Zurich, and the Swiss Data Science Center, we will develop a project to quantify the response times of river systems. So the problem here is that rivers respond very quickly to storm events, but in fact, they transport large amounts of water and solutes that are often months or even years old. So these two very different timescales coexist in river systems. The traditional way to quantify these responses that are also significantly non-stationary is by using hydrologic and transport models based on various types of response functions. These models require some a priori assumptions about how the system is expected to behave, and this certainly has an effect on the estimates, which is also difficult to quantify. So we want to develop a data-driven solution and learn the shape of the transfer function from data rather than assuming it a priori. And the Swiss Data Science Center will help us develop non-parametric and semi-parametric approaches to estimate the time-varying response time distributions for both water flow and water quality in rivers. To do so, we'll use about 40 years of meteorologic and river flow data over about 150 Swiss watersheds. And we will also use high-resolution water quality data, particularly from one of these rivers. So overall, this project will help us understand flow generation mechanisms and water quality processes.
Okay. Thank you, Guillaume. I think we can go to back to the main presentation. And now Katia, Benjamin, Michele, and Guillaume will present the call for projects. So Katia.
Thank you. I will outline the general track, which is data science for domain science. And so we welcome the projects which require the expertise of the SDSC in adopting data science and machine learning in all different application domains. So the goal of collaboration includes development and application of various methods from data science, which include areas as statistics, signal processing, machine learning, deep learning, and so on. And our work is focused on application of data science methods to real settings, which arise in different application domains. For example, biomedical sciences, environmental sciences, physics, and all others. And this year, due to agreement between PHRT and the SDSC, there will be joint funding of 2 additional projects with the focus on personalized health and personalized medicine. And so here we welcome applications for collaboration related to clinical research questions and that would have impact for patients. And these project proposals will be reviewed jointly with PHRT and SDSC. Thank you.
Okay, thank you, Katia. Benjamin?
Yeah, yes, so as it was introduced last year, so again, so we have this additional track, which is called the LSI Large Scale Infrastructure track. There was an additional budget allocation specifically dedicated for projects that are related to these large scale facilities. And this large scale facility, I'm referring to a sensor network or let's say a synchrotron or smart building like the one in NEMPA. So, and the goal of this project is the same. So we want to develop data science methods that would help both in the operational and also on the application side of the data that is coming out of these large-scale facilities. I would like to mention, though, that large-scale infrastructure doesn't necessarily mean an enormous amount of data. So in some cases, it could be the case that the data is not that large, but still the project would qualify. So not to be confused, this large-scale infrastructure with large amount of data. Yeah, so.
Okay, thank you, Benjamin. Michele?
Yes, thanks. Something that links all the projects we work on, I would say quite obviously, is actually the expertise that SDSC can bring on the table. And as Katia mentioned, we cover several aspects of data science, which ranges from statistics, signal processing, machine and deep learning, computer vision and NLP, optimization methods. And our aim is not only to help labs and PIs in selecting what is the best tool from a library of existing methods, but potentially is actually to tailoring those methods to the problem at hand. And even if needed, of course, developing new ones. In doing so, during the collaboration is of course very important that we discuss and we talk a lot, so that we can actually include what are the characteristics of the problem and the prior knowledge of a given problem into the models that we're gonna develop. And as a matter of fact, several among us, as we see the Science Center, we also not only come from a more technical background, but we also come from applied disciplines. And we do cover some subject expert matters, environmental sciences, climate sciences, for instance, biomedical images, biology, engineering, physics, so forth and so on. That simplifies the collaboration. Next slide, thanks. So the project we work on have to be planned over 2 years. And the expected mode of collaboration is very, I would say, is very what you are used to in research. So we usually lead, we are usually involved in most of the working packages of a given project, and we even lead some of those. And on a daily basis, we basically discuss our work with very frequent, which means weekly or bi-weekly meetings with the person that is so the data scientist involved in the project and the person in the lab with which we have a collaboration. So we plan our work, and usually we also have like some more, let's say, lower frequencies, all hands meetings in which we brainstorm, we plan future works, or we just simply do progress reports. Usually outcomes from those projects are the usual ones, so the usual suspects. So our aim is actually to allow PIs in their domain experts to publish influential and good papers in their domain by using data science. We also work in having like a good code and good implementation that can be reused even after the end of the project. So it's going to be important that we leave a legacy, if you want, about what we do. And then, of course, if we work on new techniques or new data science tools that are relevant also for the machine learning community at large, then other outputs will be more technical publication in specific journals of the domain. Of course, as Guillaume mentioned in the beginning of the presentation, SDSC supports open science and FAIR principles, so Renku facilitates all of that. So we want our codes to be open access, and we want our research data to be findable, accessible, interoperable, and reusable. Of course, this depends on whether it is possible, if there is like no privacy concern, if data can actually be distributed. But this will be also important as an important output, at least in my eyes. Thanks.
Thank you, Michael. So, Guillaume.
Sorry. Yes, I'll say a few words about eligibility and funding. So this call is open to PIs from the ETH domain who direct research and manage their own resources. But they can partner with either academic or industrial partners and partners who are from the ETH domain, from Switzerland or international. However, there is funding for partners that are from the ETH domain. So in terms of funded resources, the funding will cover funding for staff at the SDSC, more specifically the involvement of one senior data scientist, typically between 50% and 100%, staff in some of the applying partnering teams. And so the funding is of 120,000 Swiss francs if a single ETH domain team applies for the 2 years, and 240,000 Swiss francs if 2 or more ETH domain teams are partnering together. So as I mentioned, only personnel from ETH teams can be funded, with the following exception, that in PHRT co-funded projects, so projects on personalized health and personalized medicine, 20% of the funding that I'm describing now can fund what PHRT refers to as clinical services, and which is work outside of the domain, typically performed by clinician, nurses, or IT departments in hospitals that contribute to the data acquisition or labeling of the data. And one last thing, the PI cannot be funded. In terms of computational resources, the SDSC doesn't have its own computational infrastructure. We rely in our project on cloud compute and storage resources from Switch and CSDS. And so this has to be budgeted in the project unless the applicants would like to use their own computing resources for the project. And then finally, I'll summarize the timeline, sorry. So currently we are starting phase 1. So the 6th call is open. It was open a few days ago. So we're calling for submissions of pre-proposals that have to be submitted before July 4th. So those are 5 pages submission with a couple of additional documents like resumes, a data form that have to be submitted together at that date. These will be reviewed. This is a first phase of review, and on August 8th, the applicants whose pre-proposal was selected to go to phase 2 will be notified. And so then phase 2 begins. So in September, we will offer all the applicants in phase 2 to have a meeting with SDSC data scientists to discuss what they would like to do in the project and how we can collaborate together, so that we can also help them precise how they would like to organize their project proposal. The corresponding full proposals of 15 pages will have to be submitted by October 24th. So around the same time, we'll request to have suggestions of name of external reviewers who will join the reviewing process. The final decision on the full proposal is going to be at the beginning of February 2023 for project starting in the summer of 2023. With that, I would like to thank you for your attention, and we're happy to answer any questions that you would have.
Thank you, Guillaume. So if anybody has any question, just do what Tomislav did. Please unmute yourself and ask the question.
Hi, Fernando, and thank you everyone for preparing this nice presentation for presenting the call. I had one question regarding this contact with the SDSC data scientists. Like, can we meet with the SDSC and discuss the project ideas before pre-proposal, or we have to wait until it's actually approved in the pre-proposal to start discussing it with you guys?
So you can definitely reach out to us. Just send me send us an email to me or Guillaume, and then we will set up a meeting to discuss those ideas and help you out understand what the call is about and how to move forward in the pre-proposal. One thing that also it will be good to mention, the pre-proposal phase, usually what we are looking for is projects that have data available to be able to start on day one on the project. If you are trying to gather data and then do the project, that might be complicated, because in 24 months, getting the data and be able to progress might be complicated. So the thing that we're looking on in the first part of the proposal is that there is data, or that there will be data by the spring next year to be able to work together. That also I want to jump into Roman Fetter. He made a question that if there are projects that are scientifically independent, I would say that the goal here is to collaborate with us and help you in your project with your data science, AI, optimization, machine learning, statistics. So if you have a project that doesn't require our services, we believe that there are many other places where you can get funded for your work. Of course, every particular project, just reach out to me, and I'll be very happy to answer your questions and see if it makes sense for this call or it doesn't. And just two things: the slides and the video that we are recording will be available on the call page on Monday, together with the 2-minute videos of the projects that will be installed. Okay. And also, Martin, I would suggest that people unmute themselves and ask the question. Let me ask these two questions, and then we can go over this. Martin asked if the 240 need to be split 50-50. They can be split any way or not split at all. Whatever makes sense for the project. And yes, my email, we will send it the next time that we send an announcement, but my email is fernando.perezcruz@sdsc.ethc.ch, and Guillaume Obosinski is guillaume.obosinski@epfl.ch. Okay.
But you can also write at admin@datascience.ch if you like.
Thank you, Michele, for sharing the link for the academic projects. Sebastian, you have a question?
Yeah, hi all. Thanks for the presentation. My question is kind of old project teams so that have a finished project with the SDSC. Are they, I would assume that they are eligible as well without better or worse chances than other teams, right? And the second question would be, who exactly is eligible? Are senior scientists are explicitly mentioned, I saw in the call, but are all senior scientists eligible or only permanent senior scientists?
So Sebastian, we were very happy to work with you. So, so that's where his question is coming. He was very involved in one of the projects in the first call. What the approach that we decided to do with projects of people that are repeating is treat them as new projects. So there is no penalization for having worked with us in the past. There is not, you're not favored for having worked in the past, and that's the way that we're implementing this exploitation trade-off, being able to work with new people, but also keep those relations that have been going on. And there is people that have been funded twice, even somebody has been funded 3 times. So we are, whatever is the highest quality project in which we can help, we will be happy to have those projects. With respect to the funding, the only thing that we ask, it can be doesn't need to be a permanent scientist, but it has to be somebody that is already funded someplace else and that it has the funding to continue until the end of the project. So it doesn't need to be a permanent scientist. It doesn't need to be a professor. It's somebody that is already being covered at ETH, EPFL, or of course, EMPA, PSI, EAU, and BSL.
Hi, Fernando. I had another question regarding the budget for the PHRT type projects, because you say here that it's 20%, and that I guess would be a 20% of the total budget. So just to figure this out, I have like a scenario. So let's say that we apply with 2 ETH PIs, which would be 240 for the personnel, and then there is the SDSC personnel, which let's say it's another 130, and then there is maybe another 30K for storage and so on. So that's already 400K. Does this mean that we can then add another 100K, which would be 20% of the full budget for the clinical services, or that means that the maximum amount would be 20% of this 400K, I guess, it would be 75K.
So I think that the idea of the 20K is that it have to be, I mean, the 20% have to be part of the total budget. Of course, there is, I mean, especially the issue when we're doing for the clinical services is that the funding that we get, it comes from ETH-RAD, and they ask us to spend it in ETH-RAD institutions. So, of course, for PHRT, and we understand that for clinical services, in order to collaborate, we need to pay for the resources of getting that data. That is not easy. So the 20% should go, I would say, for the budget that you are proposing. If you need more, of course, there is always ways in which you can work with the budget. And whenever that comes in September, when we have the one-on-one meeting to discuss the final part of the proposal, we can go over the budget and see that it fulfills the criteria of the code.
Okay, so the budget is not part of the pre-proposal.
No, the pre-proposal, it should be something easy. 5 pages, you describe the problem, you describe the data that you have, and doesn't even need to go over the machine learning algorithms. You need to focus on the domain science, on your expertise. Then if the proposal have the data and it's something that we feel that we can do, then people get invited to the full proposal. And in general, the projects that do not make it to the full proposal tend to have an issue with the data, that the data is not there. So that's why we cut those projects. And then there is people that have been invited that don't have the time to submit the full proposal at the end. So when we have that process, the only thing that and then So most people make it to the full proposal. Okay, Guillaume, you want to say something before I ask you?
Yes, I just wanted to like add one element about these clinical services to clarify. So two elements. The first is that this has to represent at most 20% of the contribution of PHRT to the project. So those are projects that are co-funded with PHRT. So this is not 20% of the total amount of funding. It's 20% of the parts that correspond to staff hired in your team. So it would not be 400 in the case that you're mentioning. And the other thing is that this has to be approved by the PHRT executive committee. So I would really say that for more information of this, I would definitely encourage you to contact the the directors of PHRT. We'll be more than happy to discuss this with you.
Okay. But again, all of that discussion, there is no budget needed right now. We can have that discussion in September with us and with Danny and Francois. Okay, Mutian?
Thank you, Fernando, for the information. You mentioned briefly you're expecting this data available by next year before starting or at the starting of the project if it's funded. Just wondering, actually, we're planning something, gather the data this fall, but we won't get the data because we work with dairy cows and the climate change. And so the process is a little bit longer. So we're getting the data later this year, but by the time for pre-proposal, I won't have data, but rather a project planning to start in the fall. I was wondering how would that be seen to be evaluated for pre-proposal?
So we trust all of you. So if you tell me that the data is going to be available by spring, we will go and understand that the data will be available. So you're not going to be penalized by that.
Thank you.
Perfect. Benjamin, before you jump in, there is Sandra Debes made a question about potential collaborators. They can be added in the final proposal. So you can write your proposal by yourself. And then if you feel that you want to add more people to your call in the final proposal, that's totally allowed, and the more the merrier. So that will be happy to have more people involved. Benjamin?
Yes, so just one comment regarding the previous point about the pre-proposal that should be simple and focus on the domain science, but at the same time it should be in a language that is easy to understand for a non-domain expert, and in particular, it should describe well the problem in terms of data science. I just wanted to make this remark because that's an important point of evaluation at the pre-proposal stage.
Thank you, Benjamin. Just for reminding everybody, the pre-proposal stage is evaluated internally. There are no external evaluations. So you will have some of us senior data scientists reading the proposal, and being in a way that is for any general scientist will make the proposal easier to evaluate and move to the next phase. Guillaume?
Yes, just to add to what Benjamin was mentioning, I'd like to encourage everyone to click on the link that Michele posted, because you will find there a document called call documentation, which basically describes all the elements that we have described in this video. And since it is in written form, if some of the points are unclear to you, hopefully this should be clarified in the documentation. So I would like to encourage you to use it as a reference document. And other thing is, I'm not sure, Fernando, that we have answered the question of Amit Singh, who was asking whether a postdoc, already a data scientist working at ETH, collaborating with medical faculty, be eligible to apply for the fund. So, as I said, to be a PI for the project, you have to be a senior researcher at EPFL or ETH Zurich or one research institute, and you have to be able to manage your own funding. So, however, a postdoc can essentially be supported by a senior researcher or a professor, in the process of applying to our call. but the main applicant has to be a senior researcher or a professor or somebody who manages their own fund.
Okay, just adding to that, many of these postdoc can be copied in the proposals, and that's a way also if you are writing the proposal and you want to be credited as one of the copiers of the proposal, you can be added as one of the copiers. You're welcome, Amit. Any other comment, questions?
I have one quick question that kind of reflects one of those in the chat. What is kind of the standard way of including industry collaborators in the proposals? Is that seen as positive, or I guess they can't really have any budget, but do we then have to explain what their role is in the project and how much personnel, how much what kind of investment they're actually bringing to the project?
So I would say that the way that I would look at either industrial collaboration or somebody from outside Switzerland or outside the domain, we have projects in which people from the University of Bern or the University in Lugano have applied, or we have a project in people that work in Copenhagen on the UK have applied. So any of these will be evaluated in the proposal. So if they make sense with the proposal, it's going to be measured in a positive way. And the reviewer, especially on the second phase, the external review will see that as a positive part of the project. So I'm not encouraging anybody to add any extra people just because it looks good. It has to make sure it has to make sense in the proposal. It has to make sense in the work packages. It has to make sense in order to make the best of this project. Okay. So if there are no more questions, feel free to reach out to any of us, either through our emails or the general email that then will be directed to, oh, sorry, there is Jasha wants to have a question.
Hello, thank you for the great introduction. I have a question. I will be working at the Center for Sustainable Future Mobility, which is a collaboration of 40 professorships at ETH, and we're looking into funding from your side. And the question that we have is that essentially we want to build up a data science pipeline for our data processing, more or less. And so it's not quite a domain application, but it doesn't fall into the range of the large-scale infrastructure part. But we have these 40 groups that should use this in order to run their domain science applications. So the question is this something that we can come to you with, or should we rather go for a specific domain application?
So, I mean, I would suggest that send me an email. Let's sit down and then discuss the two things, because the way that you're explaining the first part is maybe where the Renku platform might be able to help, and then we can do something that is also more targeted toward the domain in which we can put it into this code. But I think even that your case is very specific, I would suggest send me an email. We have a meeting, the two of us, or if you want to bring somebody along, and then we decide what is the best course of action for your needs.
Thank you. That sounds very good.
Okay, perfect. Okay, so again, I will say goodbye again to everybody, unless somebody has a last minute question. Again, the video will be uploaded to our webpage on Monday. The videos for the other projects will be there too, and reach out to any of us. We are here to help. I think that's the summary that I want to transmit to all of you. Okay, so thank you. Have a good afternoon and enjoy the summertime.
Thank you, everyone.
Thank you.
Hello, everyone. My name is Kasia Arturi. I'm a data scientist working at EAVAC, and it will be my pleasure to introduce you to the Expect Mine project on behalf of all collaborators, in particular the PI, Professor Juliane Hollander. Expect Mine aims to address the challenges associated with a non-targeted high-resolution mass spectrometry analysis, which is a leading strategy for the identification of unknown environmental pollutants. The problem with the current approach lies in the fact that due to the large number of measured HRMS features, it could be hundreds or even thousands in more complex matrices, we need to prioritize what we want to identify and quantify. Today, this is done based on compounds' abundance or frequency, and while it can be useful, the approach lacks toxicological and critical in the environmental context of pollution. So to tackle this challenge, we want to develop machine learning tools, ML in vitro tox, for a prioritization based on compounds toxicity derived directly from the MS data without a structure, which would be a particular novelty in the field. Another novel aspect of the project is that we are not focusing on one toxicity type, but use a data-driven approach compiling toxicity fingerprints, ToxFPS, representing hundreds of molecular toxicity endpoints from high-throughput screening in vitro databases such as ToxCast and Tox21. Furthermore, we want not only to assess the potential toxicity of unknown HRMS features, but couple the predicted effects to the measured exposure, so the concentrations, thus assessing environmental pollutants through risks. The potential impact of Expect Mine project is truly vast. First, we want to revolutionize the environmental analysis by focusing on the compounds with the highest potential to cause harm. This would enable scientists across the globe to remap pollution in aquatic environments according to its toxicological relevance, which could become the basis for further testing and increased monitoring for chemicals of interest. We want to facilitate that by releasing the tools developed in the course of the project as open source. Thank you very much.
My name is Dimitrios Lignos. I'm a professor at EPFL, and I'm the co-PI of this project together with Dr. Nenad Bijelic from the Resilient Steel Structures Laboratory. So earthquakes are catastrophic events that, besides fatalities, have vast socioeconomic impact into our cities. And it is imperative to reliably predict the ability of structures to resist loads in the aftermath, so as we can aid repair actions in the timely manner and minimize the consequences of natural disasters. In the case of steel structures, typically damage patterns are associated with highly nonlinear geometric instabilities, as well as fracture initiation. And these failure modes can compromise the system's ability to resist loads. However, the key challenge stems from the fact that we do not know a priori what would be the reserved capacity, and visual assessment techniques would require several months to conclude that. So in the Resilient Steel Structures Laboratory, we have developed parameterized physics-based models that have been standardized with high-resolution data that you see here. In this example, we can conclude the evolution of damage in a steel component and how the physics-based models reproduce this failure pattern. So building on our expertise on physics-based models and experimentation across scales, we would like to leverage structural performance databases of three-dimensional geometries, and we would like, in collaboration with the Swiss Data Science Center, to actually predict the reserve capacity of these members through a high-resolution or high-fidelity surrogate models and a data-driven methodology. This process, we would like it to be done within seconds, thereby aiding the structural assessment process in the aftermath of natural disasters in a timely manner. So I'd like to thank you very much for your attention. I'll be happy to take any questions.
My name is Lukas Roth. I'm working as a postdoc in the group of Professor Achim Walter. In my research, I focus on the growth of wheat and the relation of this growth to climatic factors. Now, wheat is among the most important crops for food production worldwide. And in the last years, resilience to climate change has become a major issue in wheat cultivation. To mitigate these changes, we need to understand the dynamics of growth. Those dynamics are very difficult to capture by human eye, as plant growth is a very slow process. To overcome this limitation of human observations, we systematically collect images of growing crops under realistic field conditions. For this purpose, we use the field phenotyping platform FIP at ETH. The collected image time series allow us to measure and to quantify the growth dynamics of large sets of wheat genotypes. So we are able to measure growth, but the complexity of the involved steps in this analysis prevents us from systematically mining these image time series without previously defining which set of traits we want to optimize. We assume that this is strongly biasing our result, and as a consequence, we may not expect to find unforeseeable associations between growth dynamics and target rates such as yield. Now, in the collaboration with the Swiss Data Science Center, we aim to overcome this limitation. We plan to combine contemporary deep learning components with image generation models. So a neural network with convolutional and recurrent components will be trained on image time series of genotypes with a task to predict the target rate, for example, yield. The response build-up in the model's latent space will then be treated as a new trait, a so-called dynamic ideotype, which represents a characteristic growth trajectory. There are several challenges involved in such an approach. For example, we need to constrain the latent space to represent features that are hurtable. Now, this requires an intense collaboration of data science and crop phenotyping experts. And we are very much looking forward to start such a collaboration with the Swiss Data Science Center this year.
Hello, everyone. My name is Michael Kraus, and I'm PI of the project Domain-Aware AI Augmented Design of Bridge Structures. This project is a collaboration of the SDSC and the Chair of Concrete Structures and Bridge Design at ETH in Zurich. The AEC industry currently adopts generative design approaches to enable a computer-assisted design decision-making in early project stages. Existing approaches, however, largely neglect structural engineering aspects, such as design verification and construction. This holds especially true for bridges, yet they are the essential backbone of civil infrastructure. Traditionally, the bridge design is an iterative process and involves combining and optimizing many criteria and constraints for each and every individual bridge, exposing this whole process of the status quo to the threat of finding the bridge design inadmissible due to design and engineering code restrictions or constructability. So exploring multiple conceptual alternatives in early project stages is an integral and essential part of the design process and allows for the incorporation of different expectations, demands, and concerns of the stakeholders. Now, this project suggests that instead of turning input parameters until the design performance results meet certain criteria, as you can see in the figure right, which is called the forward evaluation, this research proposes to use domain-aware machine learning models of the bridge design problem, as it allows finding and exploring design instances in the proximity of specified performance goals, which now is called the inverse evaluation. This research derives agnostic methods using domain-aware AI-related approaches to tackle dimension forward and inverse problem-setting situations through the case studies of tight network arch bridges and concrete network arch bridges. The dissemination of the developed approach into engineering research and practice is provided by developing a toolkit in the form of an open source software and the generated data as a benchmark data set for the scientific machine learning community. With our proposed approach, bridge engineers in the future can more efficiently and faster predict the forward performance of certain bridge decisions and designs, and inversely design bridges due to the discovering of unexplored areas within the bridge design space and solutions that were previously intangible. Thank you for your attention.
My name is Paolo Benettin, and I am a research scientist at EPFL. Together with Professor Andrea Rinaldo from EPFL, Professor Jen Kirchner from ETH Zurich, and the Swiss Data Science Center, we will develop a project to quantify the response times of river systems. So the problem here is that rivers respond very quickly to storm events, but in fact, they transport large amounts of water and solutes that are often months or even years old. So these two very different timescales coexist in river systems. The traditional way to quantify these responses that are also significantly non-stationary is by using hydrologic and transport models based on various types of response functions. These models require some a priori assumptions about how the system is expected to behave, and this certainly has an effect on the estimates, which is also difficult to quantify. So we want to develop a data-driven solution and learn the shape of the transfer function from data rather than assuming it a priori. And the Swiss Data Science Center will help us develop non-parametric and semi-parametric approaches to estimate the time-varying response time distributions for both water flow and water quality in rivers. To do so, we'll use about 40 years of meteorologic and river flow data over about 150 Swiss watersheds. And we will also use high-resolution water quality data, particularly from one of these rivers. So overall, this project will help us understand flood generation mechanisms and water quality processes.
Hello, my name is Satoshi Takahama, and I'm happy to represent my partners, Ann Dillner and Thanos Nenes, in communicating the main ideas behind our SDSC project, cost-effective chemical speciation monitoring of particulate matter air pollution. Inhalation of atmospheric particles are associated with impaired neurological development and heart and lung disease, causing 7 million premature deaths worldwide. These particles are also critical for cloud formation and have profound influences on precipitation patterns and the energy budget of the Earth. For regulatory and scientific monitoring, mass concentrations of particles are recorded by pulling air through filters for collection and weighing them on a sensitive balance. However, atmospheric particles are complex mixtures of inorganic salts, organic matter, soot, mineral dust, and other substances, and understanding their composition at each location is necessary to identify source contributions, possible impacts. My partner, Ann Dillner, and I have demonstrated over the last decade that the same filters collected in these networks can be passed through an infrared spectrometer to rapidly acquire its infrared signature, which arises from a multitude of vibrations of molecular structures present in the sample. During this time, we've been able to show that quantitative information regarding chemical composition and source contributions can be extracted from these spectra using simple models, but each problem to be solved has its own model. So the main idea with this SDSC project is to build an open, collaborative platform and introduce modern machine learning techniques that can reduce the number and generalizability of these models by making use of common representations that can be learned from the data. This task is made possible by the more than 100,000 samples we've populated in our reference database with co-located chemical measurements in the field, together with laboratory standards that provide information on the chemical species that give rise to the observed infrared spectrum. We expect that the results of this project will lead to expansion in capabilities of monitoring networks and research groups worldwide to cost-effectively estimate particle composition, identify key sources, and support effective pollution interventions, as well as provide insight into atmospheric processes that are necessary to improve our capability for photochemical transport modeling. Thanks very much for your attention.
Hello, everybody. My name is Elena Vagnoni, and I'm glad to present you today our project Machine Learning for the Component Fatigue Prediction in Hydropower Generation, Paired Hydro. This project is a collaboration between the EPFL Technology Platform for Hydraulic Machines, the Distributed Energy Systems Laboratory, and the Swiss Data Science Center. So the main research question that this project is looking at is how to early detect and minimize the fatigue damage for critical mechanical components of Francis turbines. Hydroelectric units are more and more required to provide flexibility to the power system to allow the penetration of renewable energy sources such as solar and wind, which are unpredictable and so there is the need of balancing the electric grid. Hydropower is a perfect candidate for providing those balancing services, but of course this is not for free, because the fatigue damage due to the operation of design condition and of transient operations is actually increasing due to those flexibility requirements. So there is an increasing need to having new methods to predict the fatigue and to optimize the operation of those machines. The objectives of this project, and the solution that we propose to solve this research question is first to create a multivariate model of damage in both steady state and transient operation by leveraging years and years of data coming from reduced-scale model tests of different Francis runners that we have available in our laboratory. So by first having this multidimensional model of the damage in different operating conditions, we want then determine key indicators for the accumulated damage, in particular by looking at transient operations such as start and stop, which are the most damaging one, especially for Francis runners. Once we do have those models, that of course require advanced machine learning methods and cannot be studied otherwise with standard methods. Once we do have those model, we want to create an optimization algorithm that optimize the operating sequences. So optimization problem that define what is the best trajectory that minimizes the stresses of the damage during a startup sequence. So for instance, at the bottom right, you have evolution of the stress during time for a startup sequence of a Francis runner. What we want to see is how we can be able to determine what is the best trajectory that minimizes those stresses. The impact that we expect to have thanks to our project is to significantly cut down the operational costs, to propose new approaches leveraged by predictive maintenance, and also we expect to have a higher availability of hydroelectric unit by better supporting the energy transition.
Hello, my name is Fabian Walter and I'm a senior scientist at the Swiss Federal Institute for Forest, Snow and Landscape Research, and I am presenting here our project on the seismic detection of dangerous mass movements such as debris flows. Debris flows are mixtures of water and sediment which move down steep mountain terrain and have a significant destructive potential. Debris flows are difficult to monitor and detect because they usually occur in alpine terrain which is not very accessible. One recent suggestion is to use seismic measurements to detect debris flows, but then the challenge lies in recognizing the signature of debris flows in very noisy signals, such as shown right here. To tackle this problem, we propose to use intelligent detection algorithms, meaning that we propose a machine learning approach where an intelligent algorithm learns how typical debris flow seismic signatures look like. And in this way, it can also detect relatively weak signals and thus outperform traditional threshold-based rules. It is important that we design these algorithms such that they do not rely or only weakly rely on training data, which means that we have to employ transfer learning or anomaly detection techniques. With such an algorithm, we can leverage the vast amount of seismic data that is being acquired in real time for other purposes such as earthquake monitoring, and which is particularly densely acquired in regions where there are mountains and thus a particular debris flow hazard. The volumes of these data are continuously growing, so with our approach of machine learning algorithms for seismic detections of mass movements, we would like to leverage this continuously growing data set and thus introduce a new generation of warning systems. Thank you.
Hello everyone, I'm Alessandro Pau, a research scientist in the Swiss Plasma Center, and I have the pleasure to introduce this project that we'll be doing in collaboration with the Swiss Data Science Center. This project is about the exploitation of machine learning for the prediction of disruption in tokamaks. Tokamaks are one of the configurations with which we can confine fusion plasma by magnetic fields, and the disruptions are instead an abrupt and potentially catastrophic loss of plasma, thermal and magnetic confinement, characterized by a complex nonlinear dynamics that at the moment is not fully described by any first principle model. The way we want to address this problem is by describing plasma state trajectories in low-dimensional representation, where we are able to describe interpretable boundaries separating stable regimes from disruptive regimes. From a more technical point of view, we are proposing to build a standardized and dimensionless machine-independent representation of our high-dimensional data coming from tokamaks of different sizes currently operating in Europe, and to exploit nonlinear generative models, more in particular recurrent switching linear dynamical systems that can be fitted by using fast modular Bayesian inference algorithms in order to infer transitions from stable to disruptive regimes. And this is where the Swiss Data Science Center will play a big role. We would like also to assess the real-time capability of these models with first implementation in our TCV tokamak, and finally test the extrapolation capabilities of these machine learning tools to larger scale fusion reactors. That is the big challenge for the future, since disruptions represent the most serious concern for the exploitation of the tokamak concept for future power plants as a safe, sustainable and clean solution for our long-term energy needs.
Despite blooming research on quantum materials, many scientific questions are still open to this date. The magnetic neutron scattering probability is directly proportional to the magnetic scattering function S of Q and omega that assesses the macroscopic Hamiltonian encoding the fundamental magnetic interactions in a material. Novel multiplexing neutron instruments now allow a simultaneous probe of thousands of different points in four-dimensional Q and omega space. Thus, in a short time, a full picture of the magnetic excitation spectrum in a material can be measured. However, this tremendous improvement in the data collection generates new computational challenges. Current analysis strategies require experts to manually go through each dataset and mask out spurious background features as shown in this figure. Being a notoriously slow process, conventional analysis methods are further based on defining narrow selections around a presumed signal, while the rest of the dataset is discarded. The residual background is then modeled with a low-order polynomial. The first objective of this project is to define a non-parametric background model to enable end users to fit simulated signals directly to the full dataset. Another bottleneck of neutron scattering is that accurate simulations of the scattering process are often computationally expensive. While, for instance, detailed simulations of the instrument response function are available, they are usually not used due to the computational overhead. We aim to improve the situation by training a machine learning model on a small subset of the data. The fit can then be executed using the approximation that the resolution function is only slowly varying over the dataset instead of performing the simulation at every point. A third objective of the project is to ensure the optimal use of allocated beam time through an automated, intelligent decision-making system that will determine when sufficient data has been collected in an arbitrary measurement setting. Consequently, the experimental protocol should then advance to the next setting.
Hello, my name is Jacopo Mocchi, and I am a beamline scientist at the Swiss Light Swords at Paul Scherrer Institute. The LAMP project is a collaboration between PSI and SDSC. The problem we're trying to tackle in this project is the development of an alternative metrology method for UV mask inspection. UV mask inspection consists in the detection of defects that can be as small as 10 nanometers over the surface of the photomasks that are used for semiconductor manufacturing these days. The photomask size is about 100 by 100 millimeters. So to give you an idea of what this means, this is roughly equivalent of spotting 5-franc coin over the surface of Switzerland. Despite the challenging nature of this problem, some metrology solutions based on standard imaging approach are already existing. Unfortunately, these solutions are very expensive and they're not easily scalable as the feature size on the mask decreases following Moore's law. The solution that we propose is to explore the potential of coherent diffraction imaging as an alternative metrology approach for this problem. We already developed an end station, a microscope, that was intended to pioneer UV mask inspection with coherent diffraction imaging. What we aim to do here is to improve the existing hardware and software of this end station, which is based on standard tychography. This won't be sufficient to make this kind of approach suitable for industrial application, because we need to overcome a fundamental computational problem, and we need to ease the burden of the computation that we need to face to image these masks. So what we plan to do next is to investigate the use of a non-iterative deep learning approach to reconstruct the UV mask image from coherent diffraction data directly. This project will help us improve the current status of coherent diffraction imaging for semiconductor manufacturing metrology, and will help introducing this kind of approach to the industrial community. Thank you very much.
Hi, my name is Alexandre Coudray. I'm a PhD student in Didier Trono Research Group, and today we'll summarize you the ongoing project we have with the Swiss Data Science Center. So we're trying to predict the drug sensitivity at cell type resolution using a machine learning framework. In particular, we're interested in predicting drugs with higher efficiency to target specific subpopulation of cancer cells. So if one wants to do that experimentally, you will need to use purification techniques and then to pass the sorted cells through a drug sensitivity screening. However, this requires typically a large amount of cells as inputs and leads only to imperfect isolation of cell types. Also, it can impair the viability of cells and thus bias the drug sensitivity screening readout. So the solution we propose is to demix drug sensitivity of cell population through a machine learning framework, and therefore we can avoid any purification step and reduce the costs, and maybe also improve the accuracy. So the experimental design involves two main steps. The first one is to infer cell type proportion through a so-called Ball deconvolution method. So we're trying to push the field here and to improve existing Ball deconvolution methods. The idea of Ball deconvolution is to use gene expression to infer cell type proportion and typically rely on some single cell RNA sequencing data. Actually, the main novelty we bring is the second methods, which allows us to integrate cell type proportion previously inferred with drug sensitivity signal from the mixtures and to deconvolve drug sensitivity at cell type resolution. This is done by considering latent variables contribution to the mixed signal, and we resolve it through an expectation maximization algorithm that we were able to derive thanks to the contribution of the SDSC data scientists involved. Thus, what we are doing is to model the probability to survive a treatment of each cell type and their contribution to the observed survival rate at the bulk level. ultimately we get a prediction at the cell type level by integrating information from multiple samples. To believe this work might have a great impact in the field, we envision those computational methods could replace costly experiments necessary to screen drug sensitivity at the cell type resolution, which can be long, tedious, and expensive. Also, in the specific context of acute myeloid leukemia, we are able to predict drug sensitivity of leukemic stem cells, which is of high clinical interest. Thank you very much for your attention.
Hello, everyone. My name is Jörg Schweitzer from the SLF in Davos, and I'm pleased to present on behalf of my partners our new joint project with the Swiss Data Science Center. The WSL Institute for Snow and Avalanche Research is charged by the Swiss government to inform the public about the snow and avalanche situation in Switzerland. To that end, it runs a large infrastructure, including a network of 187 automated weather stations, located throughout the Swiss Alps. These so-called IMI stations are the backbone of avalanche forecasting. Avalanche forecasting relies on snow cover, and weather data for expert evaluation as well as for machine learning-based support tools. The data need to be accessible in high quality as soon as they become available. Any measurement errors, anomalies, and data gaps diminish forecast accuracy. However, presently the IMIS data are contaminated with data anomalies that hinder automated processing, including the application of machine learning-based support tools. Therefore, our objective is the development of algorithms that allow real-time detection of anomalies in the time series, but also should detect outliers. That means differentiate between anomalies and outliers. And finally, impute missing data by applying state-of-the-art machine learning approaches. This real-time data cleansing will solve a long-standing issue with the IMIS data, make accurate data quickly available for multiple purposes, and will in particular ease the application of models in operational avalanche forecasting as well as flood forecasting. We are grateful for the support and look forward to the collaboration with the Swiss Data Science Center.
Hello, I'm Jack Kuipers, a senior scientist in the computational biology group at ETH Zurich. And I'd like to present our project on predicting subclonal drug response in single-cell sequencing for precision oncology. This is a joint project with Professor Nico Berenwinkel, the head of the computational biology group, and Dr. Daniel Steckhoven of Nexus, also at ETH Zurich, and with the Swiss Data Science Center, of course, from whom we've had a lot of great support, and the final configuration is yet to be determined. For this project, we're concerned with tumor progression and inter-tumor heterogeneity. The tumors, over time, they develop, they evolve, and they pick up genetic aberrations, transcriptomic changes, which distinguish different cell populations, which may also divide into further subpopulations. So as a result of this tumor evolution and progression, tumors are made up of heterogeneous clones and subclones, which may be distinguished by different genetic and transcriptomic changes. This heterogeneity plays a key role in patient relapse and treatment failure, since the treatment must encompass all these different cell populations. If it's only effective for a subgroup, say the largest clone, then the smaller clones may continue to evolve and progress further, leading to relapse. The problem we wish to address is, given that tumors are heterogeneous, made up of different clones that may respond differently to different treatments, how can we predict the best treatment option for the entire tumor and for each individual patient? To address this problem, we have a large cohort of samples from 3 indications whose single cells have been profiled with 3 technologies, including single-cell RNA sequencing, which allows us to uncover the transcriptional changes in the tumor clones and to profile the immune cells, with single-cell DNA sequencing, which gives us access to copy number changes in each of the tumor clones and subclones and how they're related phylogenetically, and with the drug screening to measure the aggregated response of the tumor cells to an array of different drugs. So with the Swiss Data Science Center, we will use the underlying structure of the tumor clones and the relationship to each other to better integrate these three data facets. First, by integrating the single-cell RNA and DNA sequencing. So the integrated analysis accounts for both transcriptomic and copy number changes to extract the key features linked to drug response, and then to build a drug prediction model for each individual tumor subclone, which we can train on the overall response of all the tumor cells to each drug. With this subclonal drug prediction model, by accounting for the heterogeneity in each tumor, we aim to tailor the treatment to encompass all the subclones of each tumor in each individual patient to try to minimize further tumor progression and patient relapse, and thereby aim to improve patient outcomes.